Today's topic is the solution of differential equation of a simple harmonic motion. In the last class, we have studied what is a simple harmonic motion and the differential equation of a simple harmonic motion. A simple harmonic motion is a oscillatory motion or a vibratory motion in which the restoring force acting on it is proportional to the displacement from the mean position and is always acting towards the mean position. And the differential equation of a simple harmonic motion is given by d square x by dt square plus omega square x equal to 0, where x is the displacement of the simple harmonic motion at any instant t. And this equation is labeled as equation 1. And from the equation 1, d square x by dt square can be written as, that is, d by dt of dx by dt, where dx by dt can be represented as v, where v is the velocity of the simple harmonic motion at the instant t. Therefore, d square x by dt square becomes dv by dt. Then multiplying this equation with dx and dividing with dx and rearranging, that is dv by dx into dx by dt. Again, dx by dt will be v. Dx by dt is equal to v. Therefore, the equation will be v into dv by dx. That is, d square x by dt square can be written as v into dv by dx. That is, d square x by dt square equal to dv by dx. Dt is equal to dv by dx into dx by dt is equal to v into dv by dx. Therefore, in the equation 1, d square x by dt square can be represented as v into dv by dx. Then d square x by dt square is equal to minus omega square x, or v into dv by dx equal to minus omega square x. That is, v into dv is equal to minus omega square x. Next, integrating. That is, integral v into dv is equal to minus omega square x dx. From the standard integral x into dx, it can be written as x square by 2. Similarly, integral v dv will be v square by 2. And integral minus omega square x dx, minus omega square, and omega is a constant taking outside of the integral, and minus omega square into integral x dx. It can be written as minus omega square integral x dx will be x square by 2 plus a constant of integration. That can be represented as c. That is, c is the constant of integration. To find the value of c, we are applying a limit. That is, when x equal to a at the extreme position. X means is the displacement. Here we are considering the value of x at the extreme position. That means the maximum value of the displacement. That will be the amplitude. That is, the maximum value of the displacement x equal to a. A is the amplitude. Then at the extreme position, when x equal to a, the amplitude, that is, a is the amplitude. Then the velocity will be dx by dt. Here, if x tends to a, where a is the amplitude and it's the maximum value of x, then the constant a is a constant. Then we get d by dt of the constant a. It will be 0. That is, at the extreme position, when x equal to a, v will be 0. And applying this condition to the equation, that is, 0 is equal to minus omega square a square by 2 plus c. That is, v will be 0. In this equation, v will be 0 at the extreme position. And therefore, 0 is equal to minus omega square. X becomes a square divided by 2 plus c. Or c can be written as omega square a square by 2. Therefore, the equation will be v square by 2 is equal to minus omega square x square by 2 plus omega square a square by 2. Or the velocity of a simple harmonic motion can be represented as v square is equal to omega square into a square minus x square. Or v is equal to omega into root of a square minus x square. And this gives the velocity of the particle at a point x from the mean position. But the velocity v is equal to dx by dt. Therefore, this equation can be written as, that is, dx by dt is equal to omega into root of a square minus x square. Or it can be written as dx divided by root of a square minus x square is equal to omega into dt, where dx divided by root of a square minus x square, and integrating this term. This is a standard integral and its value will be sine inverse x by a. That is, integrating this equation we get sine inverse x by a, and integral omega dt. It will be omega into integral dt, that is t, omega t, plus phi, where phi is the constant of integration. Therefore, this equation can be written as x by a is equal to sine omega t plus phi. Or the displacement of the particle at an instant of time t, x is equal to a sine omega t plus phi. That is, this is the solution of the differential equation d square x by dt square plus omega square x equal to 0. This equation gives the displacement of a particle at any instant t. Expression for the acceleration of a simple harmonic motion. The differential equation of a simple harmonic motion is given by d square x by dt square plus omega square x equal to 0. Or d square x by dt square is equal to minus omega square x. Therefore, the acceleration of a particle executing the simple harmonic motion A is equal to d square x by dt square, and it can be written as minus omega square x, where omega is equal to 2 pi by t or root of k by m. And considering the two different cases, one is at the extreme position. At the extreme position, the value of x will be a. Therefore, this equation will be minus omega square a. That is, at the extreme position where x equal to a, the acceleration will be maximum. And this maximum value of acceleration can be written as a max is equal to minus omega square a. At the mean position where x equal to 0, the value will be minus omega square into 0. That is, it will be 0. That is, at the mean position where x equal to 0, the acceleration is minimum. And the minimum value of the acceleration will be a minima is equal to 0. Next is the expression for velocity of simple harmonic motion. The velocity of a simple harmonic motion is given by v is equal to omega into root of a square minus x square. And at the extreme position where x equal to a, the velocity v is equal to omega into root of a square minus x will be a at the extreme position, therefore a square. That is, it will be 0. That is, at the extreme position where x equal to a, the velocity will be 0. That is, the velocity is minimum at the extreme position. Considering the mean position where x equal to 0, the velocity v is equal to omega into root of a square minus 0. Or it will be omega into square root of a square, it is a. That is, at the mean position where x equal to 0, the velocity is maximum, or the maximum velocity Vmax equal to omega into a. Therefore, the velocity is maximum at the mean position and the acceleration will be minimum at the mean position, and the velocity is minimum at the extreme position where the acceleration is maximum at the extreme position. That is the case of simple harmonic motion.